Hello and welcome to compound events and independence. Compound events just simply means when you have more than one event happening together, and independence we're going to look at in a moment. For the moment, copy down this part of the screen. Go ahead and pause it. And now I will explain. An event is just any set of outcomes. We talk about outcomes being anything that can happen. So if I were to roll a die and I say, what's the probability of getting an odd number? Well, that event would be the set of outcomes that are odd. So 1, 3, or 5 would be that event. It could only be just one outcome, or it could be more than one outcome. But anytime you have a group, or just even one of them, we call that the event. And the theoretical probability, we've talked about the probability. We would read this as the probability of the event happening is equal to the desired outcomes, the ones that we want to see happen, divided by the total outcomes. So this is the sample space that we've been talking about. So all the possible things that could happen. And this is the ones that we want to have happen from the event. So for example, if I wanted to say, what's the probability of rolling an odd number? Well, how many odd numbers are there? There are 3. Out of the total possible sample space of 6, so 3 out of 6, the probability is 50%. Now, complementary event is basically the opposite of the event happening. It's the outcome not happening. And so if E is the event, we would write this little E prime, we write that little notation there, that means the complement, that means not E. So the probability of E happening plus the probability that it doesn't happen equals 1, because it always equals 100%. The probability of it raining today and it not raining today adds up to be 100%. Always. So if I subtract the probability of E, we can find E complement is equal to 100, or 1, minus the probability of E happening. And we're going to use that as we move forward. Okay, here's an example. One card is randomly selected from a pack of 52 playing cards. Determine the probability that it is an ace. So to find the probability that it's an ace, we need to think how many aces are there in the deck divided by how many total cards. There are 4 aces and the sample space is 52. So we've got 4 out of 52. I'll grab my handy dandy calculator. We would like to reduce this if we can. So this reduces to be 1 out of 13. So the probability of drawing an ace is 1/13, which is 0.076, or 7.6%. We usually leave it like this, though, but that's okay. The probability of not an ace. Okay, that's probability. We could not an ace. Okay, what's the probability of that happening? Well, we know that 4 are aces, so how many are not aces? 48 other cards are not aces. We could reduce this to be 12/13, which is, as a decimal, 12 divided by 13, 923, or 92.3%. So these should add up to be 100%. All the cards that are aces and all the cards that are not aces should add up to be 100%, all the cards. Probability of a picture card. That means a jack, a queen, or a king. So probability of a picture card. I'll do this. How many jacks, how many queens, how many kings? There are 3 jacks in each suit. There are 4 suits, so 3 clubs, 3 spades, 3 hearts, 3 diamonds. That leaves a total of 12 picture cards in the deck out of the 52. Can we reduce this? I think we could divide this here by 4, and that would leave 3/13. And 3 divided by 13 is 0.23, or 23% of the cards in the deck are picture cards. The other important idea here is if 2 events are independent. We would call them independent if the outcome of one event does not affect the outcome of the other effect. If you've got 2 things that are unrelated. Sometimes the outcome of one event does change the outcome of the next one. If I reach into a bag and I draw a blue, and then I reach in again, well, now there's not another blue in there, so my first action affects the probability of what's happening next. But if that doesn't happen, if we have two things that don't affect each other, they're called independent. And if they are independent, then to find the probability of them both happening together, we can just multiply them together. So here's the rule. If they are independent, then the probability of A and B together is equal to the probability of A times the probability of B. Here's an example. A coin and a die are tossed simultaneously. Okay, does the coin, being heads or tails, affect or change the number that comes up on my die? No, this could be whatever it's going to be, and this could be whatever it's going to be, and the two things don't affect each other. So they are independent. So if I could find the probability of getting a head, then I could multiply that by the probability of getting a 3, because they are independent. And the probability of getting a head, I have a 1 out of 2 chance. The probability of getting a 3 when I roll a die is 1 out of 6. So together I have a 1 out of 12 chance of getting both heads and a 3. I could divide this up on the calculator, 1 divided by 12, and I get 0.083. Okay? Those are independent, so we can use that rule. All right. Next one. Suppose a hitter has a 300 batting average. That means that 3 out of every 10 times that he comes up to the plate, he's going to get a hit. His probability of getting a hit is 30%. Now, are those independent if he gets 3 hits in a row? Does getting the first hit affect whether or not he gets the next hit, affect whether or not he gets the next hit? Now, this one's a little bit tricky because some people might argue, well, if you get a hit the first time, you're more confident, and the second one, then you're a lot more confident, and you're ready, so there's a psychological effect. But let's suppose that there are 3 different pitchers. Let's suppose that it's maybe 3 different days, and we're just getting 3 hits in a row. So whether he gets the first one does not affect the probability of the next one, does not affect the probability of the next one. If they are independent, if we're not thinking about the psychological advantage, just the math part of it, then they are independent, and we could take the probability he gets a hit the first time, times the probability he gets a hit the second time, times the probability he gets a hit the third time. Probability he gets a hit the first time is 30%, so that's 0.3 times 0.3 times 0.3. 0.3 times 0.3 times 0.3, we can do that on the calculator. And I get 0.027, or in a percentage, a 2.7% chance. So even a 300 hitter who's pretty good, if he goes 3 for 3, you think, what are the chances of that happening? Only a 2.7% chance. It's pretty unlikely that he's going to do that. That's how it works with independent events. If we can find that they don't affect each other, then we just multiply them. Have a great day.